Hello viewers, welcome back to my channel. In this video we want to talk about introduction to complex variables. Then this is the fourth video we are making on this particular course. So the first three videos we discussed about complex number in general, like a prerequisite to this particular course. Okay, that is the things you need to know before we enter the main course. Okay, so we're about to enter the main course now. So but a recap to what I thought, we talked about a complex number, the definition of a complex number, the forms of a complex number. Okay, how you can express a complex number in the Cartesian form or the polar form or the exponential form or logarithm form. So we now talked about operations of complex number, that is addition, subtraction, multiplication, division, where division led us to rationalization of complex number. So we now talk about the Movian theorem and its application. Okay, how to find the powers of a complex number, how to find the nth root of a complex number, then and so many other things that we talked about. So, but in this particular video now, we are going to be talking about how to express a complex variable. We are now moving from complex number to complex variable. And you can remember that a complex number has both the real and the imaginary part. So the same way a complex number has both the real and the imaginary part is the same way a complex variables has the real, can be expressed in real and imaginary part. Okay, so that is the first thing we're going to be looking at, how to express a complex variable, not a complex number, a complex variable into the real and the imaginary part. Now when they're talking about a complex variable, they're talking about function of a function. If, for example, if w is equal to a function of z, okay, and then we know that this function of z is can be expressed as u, which is a function of x and y, okay, plus I v, which is a function of x and y. So when you have that, a function of another function, you call it complex variable. So we want to look at how to express a function like this into real and imaginary part. Okay, for example, if you are given exponential z, you know that this is a function of z. So how do you convert it into real and imaginary part that is a function of x and y? That's the first thing. So from there we'll now move to differentiability. Okay, the differentiability of a complex number. How do we differentiate complex number? So from there we'll now move to analytic function. So how do we know that a complex number is analytic? Okay, within a particular point or region. Okay, so from there we will now look at harmonic function. Then we are done for this particular video. So let's get right into the video. So the first one is how to express a complex variable. Express a complex variable into real and what? Imaginary part. Okay, so now example, just go straight. That is what we are trying to talk about. Is if you are giving maybe w is equal to a function of z. If you're given a function of z, you are now required to turn it into u, that is a function of x plus y, plus iv, that is a function of x plus y. If you look at it, you see that this one that does not have I is the real part. This one that has I is the imaginary part. Okay, so let us take some questions to illustrate what we mean by that. So the first question here says that express the following into the real and the imaginary part. So that's the question. Express the following into real and what? Imaginary part. Okay, so the first question said that f of z is equal to what? Z squared. Okay, f of z is equal to z squared. So this is very simple. Solution. So we are given that f of z is equal to what? Z squared. So, and we know that z is equal to what? S plus yi. So if I put it here now, you now see that f of z will now be equal to what? X plus yi all squared. Okay, So to open this bracket, this is going to be the same thing as this multiplied by itself. Or you do the shortcut that says square the first one, multiply the first one and the second one, double it, and square the last one. So square the first one, x squared. Multiply the first one and the second one, xyi. Double it, you have what? Plus 2i xy. So square the last one, you're going to have, that is yi all squared. So this is going to be x squared plus 2ixy plus, remember that I squared is minus 1. So here we now turn to minus, then y squared is y squared. Okay. So if you look at this very well, you see that this can be expressed as s squared minus y squared. These people, they don't have I. Then plus what? 2i x y, or 2xyi. Anyone? 2xyi. So if you look at this, you will now notice that your u of x comma y is equal to this one that does not have the real part. This one is the real part, which is the one that does not have I. Then your v comma x comma y will now be this part that has I, which is what? 2xy. So you have expressed this complex number and this complex variable into your x and into your real and imaginary part. Okay, as simple as that. So we'll take the next question. This is question number 1. So when we solve about 3 or 4 questions, you will understand better. So for question number 2, we are given that z is equal to, we have given that a function of z is equal to exponential z. Now don't forget again that z is equal to what? S plus yi. So if I put it here, you see that f of z is equal to what? Exponential x plus yi. So if you open the bracket here, you see that you are going to be having that this is equal to exponential x multiplied by exponential yi. Okay, because according to the law of indices say that if the base are the same thing, we should add the power. If the base are the same thing, we should add the power. So 2 plus 3. Okay, so which means when you have 2 plus 3, you can change it back to, and you have multiplication, not addition. So you can change it to the first one raised power x raised power 2, then multiply by x raised power 3. So according to indices. So if you leave this one this way, exponential x, don't forget that exponential I theta is something as saying what? Cos theta plus what? I sine theta. So this one can be written as what? In bracket of cos y plus I sine y. So if I open this bracket, you see that I'm going to be having exponential x cos y plus I exponential x sine y. Okay, so obviously you see that u of x comma y, which is the real part, is equal to exponential x cos y. That is the part that does not have I. Then v of x comma y is equal to what? Exponential x sine y. Okay, so that is just that, as simple as that. So we move to the next question. Question number 3. Question number 3. So for question number 3, we have that they gave us that f of z is equal to 1 over z square. Okay, 1 over z square. So now this is very, very simple. What do we do? The same method, it does not change. So we are going to have the same method and it does not change. So we are going to have what do we have now? So we know that our z is equal to x plus yi. So if I put it here, I'm going to have that f of z will now be equal to 1 over x plus what? Yi all squared. So if I open the bracket of squared, I'm going to be having that this is equal to 1 over square the first one, x squared. Multiply the first one and the second one, double it. You have what? 2xyi. Square the last one, you have minus y squared. We have done it before. So if you separate this, you see that you are going to be having 1 over x squared minus y squared, then plus what? 2xyi. Now remember, I taught you rationalization of complex number. I told you that anytime you have a complex number at the denominator, you have to rationalize so that it will disappear. So it's an abomination for us to leave I at the denominator. So we have to rationalize this. So to rationalize this, I'm going to have that this is equal to 1 over x squared minus y squared then plus 2xyi multiplied by the conjugate. So this is the real part. So multiply by the conjugate. The conjugate will give us x squared minus y squared then minus 2xyi like this. Okay, so all over the same thing. X squared minus y squared then minus 2xyi. Okay, so from here we will now multiply out and get our. Sorry, I didn't know that I did not on my mic. So what we did was just rationalization. 1 times anything is the same thing. The denominator of rationalization of a complex number is always in the form of difference of 2 squares. So you say the first one times the first one, then minus the second one times the second one. But 2 times 2 is 4. X times x is x squared. Y times y is y squared. So here's supposed to be minus, but I times I is minus 1. So that minus 1 is what will make this place plus. Okay, so you now separate the first people. Now this one that does not have I all over everything minus this one all over everything. So you see that this one that does not have I is our real part. So you see that your u of x comma y will now be equal to x squared minus y squared all over x squared minus y squared all squared plus 4 x squared y squared. While your v of x comma y now be equal to this minus 2xy all over x squared minus y squared all squared plus 4 x squared y squared. So that is that for this particular one. So we move to the next question. Okay. So question number 3 or question number 4 rather. Okay, question number 4 said that W is equal to sine Z. Don't forget that your Z is equal to x plus yi. So if I put it here, I will be getting that W is equal to sine x plus yi. So which is, if you remember trigonometry, they are the sine rule that sine A plus B is equal to what? Sine A cos B plus sine B cos A. Okay, so if I do the same thing here, you will now see that your W will now be sine X cos yi. Okay, cos yi, then plus sine yi cos X. Okay, now I remember that I told you that that cos is an even function. So this I will disappear, and then this trigonometry will not change to hyperbolic function. Okay, hyperbolic function of trigonometry. The same thing here. So because of the I inside here, it will change to hyperbolic, but the I will come outside to show that sine is what? An odd function. So this will now give us W is equal to sine x. The I can disappear to now turn to cos y, okay, plus sine y cos x. But don't forget that because sine is an odd function, the I will come outside here. So you see that your u of x comma y will now be equal to what? Sine s cos y, while your v of s comma y will now be equal to what? Sine y cos x. As simple as that. So we'll solve the last question on this, then we'll now move to differentiability and analytic function. So the last question I'm going to be solving, I don't know why. No, okay, let me peg it. But I always like it because I want to see when it will off. Okay, so the last question say that f of z is equal to what? Cos z. So don't forget that your z is equal to x plus yi. So if you put it here, you now have that f of z is equal to what? Cos x plus yi. So if you open the bracket according to cosine rule, that cos a plus b is equal to cos a cos b. If there is plus, it will be minus sine a sine b. So if you remember this now and refill my marker, so tell me what the answer will be at the comment section before I solve it. Okay, using the hyperbolic function and the odd and even function. So tell me what the answer will be at the comment section. So from here, I'll see that my f of z will now be equal to cos x cos yi minus sine x sine yi. So I thought that cos is an even function, so the I will disappear, but this one will change to hyperbolic. It will now be what? Cos x cos y minus the I will come outside because sine is an odd function. I will come outside. I will now have sine x sine y. Okay, so and that is that for that. So we'll now move to differentiability and analytic function. Now, for differentiability, in fact, if you know the normal method of differentiation, it's the same thing with here. So you can watch my video on differentiation so that we don't waste time on that. Okay, but you should know that definitely know that if f of z is what? Single valued function. F of z is single valued function. Okay, in a region, in some region R of the z plane, then the derivative of f of z is defined as the same first principle, differentiation by first principle. So the derivative is defined as f prime of z is equal to the limit as change in z tends to what? Tends to 0. Okay, as the limit approaches 0 of f of z plus change in z, then minus f of z, then all over the same change in z. So if this limit exists, then we'll conclude that what? That f of z is differentiable. Okay, so if this limit exists, we conclude that f of z is differentiable. So there is no big thing here. If you know differentiation by first principle, you will understand. It's the same thing here, or the normal differentiation. Sometimes they may ask you to use first principle, or they ask you to use normal differentiation. Okay, so I won't go details into that because we don't have time. So just go and watch my video on differentiation. The link I may put it in the description, or you go to the playlist side of my channel, you will see differentiation. I did a very good job on differentiation. Okay, so go and watch that. So let's move to analytic function. Okay, so for analytic function, you should know that a function f of, right, okay, let's write a function. Okay, now when do we say that a function is analytic? It's simple. A function is analytic at a point, at a given point, maybe s naught, okay, or at a given point a. A function is analytic at a given point a if that function is differentiable. Remember what I talked about differentiability. Is differentiable at that particular point and equally differentiable at the neighborhood of that particular point. So it is not only differentiable at that point, it should equally be differentiable at the neighborhood of that point. So don't mind the way my eyes is because if you check my time now, is I think after 2 or after 3. So I like doing my video by this time of the day when my children is asleep, okay, so that they will not distract the video. Okay, so like I said, that a function is analytic at a point, maybe z naught or a point a, if that function is differentiable at that point z naught and equal differentiable at the neighborhood of that z naught. Okay, so let us write that a function f of z, okay, is said to be analytic. Okay, since I've said it, just write it so that I will not waste time. So to illustrate this, let's have this function. Okay, let's have a function like this, for example, and then we are given a point. Maybe we are given this point. Let's say that this point is our z naught. So let's treat this point to be our z naught. Okay, so now if this function is differentiable at this z naught and equally differentiable at the neighborhood, maybe here, let me say there's another point here, and that point is just a little change in z naught, and then here, maybe somewhere here, okay, a little change in z, let's say z1, z2. So if it is differentiable at those points, okay, if the differentiation exists, if the limit at this tend to this, blah blah blah, exists, then we'll now conclude that what it is analytic. But there is a way to show that a function is analytic. You don't need to start checking the differentiation of the neighborhood, blah blah blah. So there's a way to check it. What we use in checking it is that differentiation by first principle. So we use differentiation by first principle to check it. So if I have that our f of z, but before you do that, you have to put it in terms of, that is why we learned that first thing I taught you. That is how to separate or how to express a complex variable into the real and the imaginary part. So that complex variable is supposed to be in real and then imaginary part before we can now test for analyticity, okay, or to check if it is analytic. Now, how do we check it? Let's recall, okay, recall that the f dz is equal to f of, don't forget, okay, sorry, is equal to the limit, or let me call, okay, the limit as delta z tends to 0 of what, f of z plus that delta z, okay, minus f of z, then all over delta z. Okay, so we know this. So since we know this now, let us put our z. We know what is our f of z is. Okay, so now, so we know that our z is equal to x plus yi, yi. So which means if I add delta to the both of them, so if I have, therefore z plus delta z will now be equal to x plus delta x, okay, plus y plus delta y, I. Okay, so something of this nature. So if I do that, and then, or we even know, sorry, z is not equal to this. Yeah, z is equal to this. So but so to come to this part now, you will see that f of z plus delta z, okay, will be equal to, here, add it here. So you have u of what? X plus delta x, comma, you now have what? Y plus delta y. Okay, y plus delta y, then plus, because you know normally that f of z, where is it? Okay, I've even written it here. So plus iv of x plus delta x, comma, y plus delta y. Okay, so if we put this thing here, we are going to be having that the f dz the f dz is equal to the limit as delta z tends to 0 of now. Okay, uh since we're having delta z here, we can change it as delta x tends to 0 and delta y tends to 0. Okay, so let's change it to this, of f of this. So f of this is this. So let us just put everybody. So f of this plus this is equal to this. So let us put it. So this is equal to u of x plus delta x, comma, y plus delta y. Okay, then plus I v in bracket of x plus delta x, comma, y plus delta y. Okay, this will not enter. So let me clean the board and write it to be very long, so that you will understand it perfectly. Okay, so let's take it gradually so that we will not make a mistake. Okay, so we have we just want to form everything we are seeing here like this. Just want to form everything we are seeing here like this. Okay, so to form that, or let us even start from, we know that f of z, let's start from here, that f of z is equal to what? U of x plus y, sorry, u of s comma y plus I v of s comma y. Okay, so remember that we have something in mind. What we have in mind is to get the lim as delta z approaches 0 of f of z plus delta z minus f of z all over delta z. So, sorry. So this is what we have in mind. So from here, so since we have uh, f of z plus delta z, so let us add delta z to everywhere. So I'm going to have f of z plus delta z will now be equal to what? So first all this rubbish I wrote here. So first all this rubbish I wrote here. Okay. So what do we have now? So we have that this is equal to, so let's add u of what? X plus delta x, comma, y plus delta y. Okay, then plus iv in bracket of x plus delta x, comma, y plus delta y. Okay, so we have this. Now the next thing we're going to do is what? To subtract this from it. To want to remove delta z from here. So I'm going to have that f of z plus delta z. I'm subtracting f of z from it. So is equal to u of x plus delta x, comma, y plus delta y. Okay, plus iv in bracket of x plus delta x, comma, y plus delta y minus f of z. And remember that f of z is the same thing as this. So instead of me writing f of z here, let me write the same thing here. Let me write u of x comma y minus iv of x comma y. So the minus here is because I have opened the bracket, because it's supposed to be minus in bracket of these people. So if you open bracket, minus times this is the same thing. Minus times plus, we change it to minus. So the next thing we're going to do is to divide both sides by delta z. We want to get exactly this, to divide both sides by delta z. So if I divide both sides by delta z, I'm going to be having everybody here divided by delta z. So everybody here divided by delta z is the same thing as saying delta x plus delta y, because I know that z is equal to x plus y. So delta z is same as saying delta x plus what I delta y. Okay, so let me write it as delta x plus I delta y. Okay, so having this, so what is the next thing we are going to do? So we're going to take the limit of as z tends to 0 on both sides. So I'm taking the lim of f of z plus delta z, okay, minus f of z all over, sorry, all over delta z as delta z tends to 0. So is equal to the lim of all these people, the lim of u in bracket of x plus delta x, comma, y plus delta y, okay, plus iv in bracket of x plus delta x, comma, y plus delta y, okay, then minus u of x, comma, y, u of x, comma, y, then minus iv of x, comma, y, okay, all over delta x plus I delta y. So remember that the lim of this, I can change this to these two people. So I can say the lim as delta x tends to 0 and delta y tends to 0. Okay, so when we have these two things, then we are good to go. So the first one is to take the first limit, and then we'll now take the second limit. Okay, so let's now take the limit as delta x tends to 0. So if you're taking the limit as delta x tends to 0, you will see that, in fact, all this place is the same thing as saying, all this place is the same thing as saying partial f over what? Partial z. Okay? So partial f, partial z. So that is this. So this is equal to, now we want to take the limit as delta x tends to 0. As delta x tends to 0. So that means anywhere I see delta x, I'm going to put 0. Let me just write it out so that you know what we are doing. So take the lim as delta x tends to 0. So you know that normally everything here is going to be partial f over partial z is equal to. So we are putting 0 anywhere we see what is it called? Okay, before we do that, we need to separate this into real and imaginary parts. So that's the error here. So we need to separate it into real and the imaginary parts so that it will make sense. Or we'll make everybody over this. So this over this, this over this, this over this, this over this. So that everybody will stay on their own. Okay, so let us have that. Or just have in mind, because of the nature of my board, the next step before you take the limit is just to say this over this, this over this, this over this, this over this. Okay, so as delta z is tending to 0, so anywhere we see delta x, now we're putting 0. So we're having that this is now the lim as delta y tends to 0. Okay, the lim as delta y tends to 0. Now this one is out. So being out means that anywhere we see delta s, I can now put 0. So this will now be u of x, comma, y plus delta y. Okay, u of x, comma, y plus delta y all over. Remember, each of them is divided by this. All over. This one is out. I'm left with I delta y. Okay, so I'm left with I delta y. So the next one is going to be what? The next one is going to be plus. Here will now be what? iv into x, comma, y plus delta y. Okay, all over I delta, all over I delta y. Okay, so the next one is this side now, minus u of x, comma, y, then I delta y. Then this side will now be iv of x, comma, y over what? Delta y. Okay, so now if you look at this thing very well, we're going to have so let us now put it in a way that it will now make sense. So what do we do now? We are going to have okay, let's take these two. Okay, there's I here. Okay, so I here is taking care of I here, and I here is taking care of I here. So I'm going to have that this thing is something as the lim as data y tend to 0 of what do we have? Okay, the lim of this, then we're going to have what do we have here? So we don't keep I at the denominator. So if I rationalize this, we're going to have okay, if I rationalize this one now, okay, sorry, this one will, I here will take care of I here, and I here will take care of I here. So I am left with this one, which is what? V of x comma y data, sorry, y plus data y, okay, y plus data y, minus his brother, which is v of x comma y all over. They both have the same denominator in common, so delta y. That is how this one will look like. Then I'm going to have, if I rationalize this side, it's going to be plus, so this is plus. If I rationalize this, I did that if you have minus 3 over 2i, so the easiest way to rationalize is if you bring the I up, change the sign here. So the minus is going to be 3 over 2 plus. I will now bring the I up. So if I want to bring the I up here, this one will change to plus, so it's going to be plus. So if I want to bring the I up here, this one will change to minus. So I'm going to, okay, let me bring out the minus outside. Okay, there's minus outside here. So this is going to be, remember, this place is negative, so it's going to be positive now. So which is what? U of x comma y plus data y all over what? Data y. Okay, minus where is his brother? This person, which is u of x comma y all over what? Data y. Okay, so you will now see that minus times this will give you this one, and minus times minus will give you this one as plus. And remember, why this one became minus is if you rationalize, you change the sign. Why this one became plus, if you rationalize, that is if you take I up, the sign will go. Okay, so from here now, we can separate the limit of this one and the limit of this one. Okay, so the proof is too long. So I'm having here to be what? Delta f over what? Delta z is equal to. So this side is going to be so this side is going to be so 1 minute. Let me check something. Okay, so this part is going to give me now. Here is the same thing as saying, if you look at here is something as what? I said that the limit of this is something as delta f delta z. So the limit of this one is going to be what? Delta is going to be delta v delta y. So that is what here will give me. Okay, delta v delta y. So it will now be, so this will now be partial v over what? Partial y minus, this one will give me what? Partial u partial y. So minus partial u partial y. Okay, so that's what this one gave me. So now let me clean here and then take the limit as delta y tends to 0. So the next limit I'm taking from here again, want to now take the limit as delta y tends to 0. So that means here will give me partial f partial z is equal to, so here will give me, that means anywhere we see delta y, we'll put 0. So 0 will now be here. So I'm having u of x plus delta y, delta x, comma y over, here is now 0. So I'm having delta x left here. Okay, and that is for these two people. So for these two people will now be plus iv of what? X plus delta x, okay, then comma y all over delta x for these two people. So for these two people will now be minus u of s comma y over what? Delta x. So these last two people will now be minus iv of x comma y over what? Delta y. So you will see that the u people bring the u people together and they have the same denominator. So partial f over partial z will now be u of x plus delta x comma y minus u of x comma y all over delta x plus, bring the v people together. They have I will now be outside. So they have I in common. So I have um, v in bracket of x plus delta x, okay, comma y, then minus v of x comma y all over delta x. Sorry, not delta y. All over delta x. Okay, so now you see that for the second part I have that the same partial f partial z. This one is giving me, this side will now be partial u partial x. So this is now partial u partial x. So this one will now be partial v partial x. So but there's I in it. Sorry, I forgot that there is I in the other one. Remember when I rationalized, the I was up, so I forgot to put it. Please go back to your note and put it in the other side. I think I don't know which of the side again. I don't know if it's the V part. So let us check if we are putting 0 here. So I okay, the I was on the U part, yes, because on the V part, I up here, I down here cancelled each other. I up here, I down here cancelled each other. So it was on the U part. Okay, so this is now plus, this will now give you what? I partial V partial X. Now you see that these two things are equal because this and this are equal. So equating the two of them, I'm going to be having partial v over partial y. Okay, well, let me write this first one. Partial u over partial x plus I partial v over partial x is equal to this one. Partial v over partial y minus I partial u over partial y. Okay, so let us equate the real part and then equate the imaginary part. So equate the real part, we are going to have partial u over partial x is equal to what? Partial v over partial y. Okay, so then the next one, equate the imaginary part, you have what? Partial v over partial x is equal to what? Minus partial u over partial y. So this is what we called the Cauchy-Riemann equation. So this is how to prove Cauchy-Riemann equation. Now, a function is analytic if that function can satisfy the Cauchy-Riemann equation. So if you don't understand all this proof, just come down, let us solve example. Just learn the example if you cannot learn the proof. But because sometimes they may not ask you to prove it, they can just ask you to test the analyticity of a particular function, or to check if a particular function is analytic. So how to test that a function is analytic is that if you satisfy this Cauchy-Riemann equation. Okay, so write that in this Cauchy-Riemann equation. So let us solve example to illustrate that. Now, how do I remember this Cauchy-Riemann equation? Because most of the times I get it wrong, that I will now put minus in this one and put plus in the other one. So how do I know? How do I remember it? I remember it when they are proper, they will not have minus. Proper, I mean in the sense that partial u came before v, u came before v, and then s came before y. So if it is this real part normal, partial u partial x, it will be equal to partial v partial y. Normal, there won't be minus. But if it is partial v partial x, it will not be minus of partial u partial y. Or if you say partial u partial y will be equal to minus partial v partial x, anyone you like. So when they are not proper, you remember they will be minus. But if they are proper, they won't be minus. So that is how I do remember it. Okay, so let us now solve some questions to illustrate what we have been writing so far. So to test the analytic part of analyticity of a complex analyticity of a complex variable, we don't really need to follow this whole process of derivation. So we just have to check that few particular thing, then we are good to go. So the first question said test the analyticity of f of z is equal to 1 over z. Okay, so this is a very simple question solution. I thought that the first thing you do is to express it into the real and the imaginary part. That was why I taught you that first. So after expressing it into real and imaginary part, then the next thing we're going to do is now to to uh to do the needful. Okay, so let's go by expressing it. So I have f of z is equal to what? 1 over z. But don't forget that your z is equal to what? So this thing f of z is equal to what? 1 over z is something as s plus yi. And I told that I can never be at the denominator. We must do what? Rationalize. So if I rationalize, I'm going to be having that this is equal to what? 1 over x plus yi times the conjugate, which is what? X minus yi. S minus yi over the same s minus yi. So if I multiply out y times anything, it's still the same thing. X minus yi all over the denominator is always difference of two squares. So x times x squared, plus times minus y times y squared, I times I minus 1. That minus 1 will now make it to be plus. Okay, so you now separate it into real and imaginary. So I have x over x squared plus y squared plus minus minus y over x squared plus y squared I. Okay, so you now see that from here you will now notice that your u of s comma y is equal to x over s squared plus y squared. Okay, and then your v of x comma y is this part that has I, which is what? Y over s squared plus y squared. Okay, so now the next thing we are going to do is to get our partial this, then we are done. Okay, so we write out the formula. Our formula is always what? That partial u over partial x, the normal one, will now be equal to partial v over partial y, normal one. But if it is partial u over partial y, abnormal, will now be negative partial v over partial x, so abnormal. So let us now get our partial u, partial x. So partial u, partial x, there is x in both sides. So it is called quotient rule. So if I use quotient rule, the shortcut said start with the denominator and end with the denominator. So we are starting with the denominator and we're going to end with the denominator. And they said leave the denominator, differentiate the numerator, minus, leave the numerator, differentiate the denominator, all over denominator squared. So if you can say this thing, you can do it. That's the shortcut. Leave the denominator, differentiate the numerator, leave the numerator, differentiate the denominator, all over denominator squared. So I'm going to have leave the denominator, that is x squared plus y squared. Differentiate the numerator, I have 1. Differentiation of x is 1. Minus, leave the numerator now. Differentiate the denominator, I'm going to have 2x. So then all over that same denominator squared. S squared plus y squared, all squared. So if you open the bracket, you're going to have this time this will give you minus x squared. S squared minus 2s squared will give you minus s squared. So I'm having y squared minus x squared all over s squared plus y squared, all squared. Okay, so now let us get our partial u, partial v. So partial u, partial x, partial y, partial u, partial y is the same quotient rule again. Okay, so let's try the same quotient rule. And this one said leave the denominator, that is x squared plus y squared. Okay, leave the denominator. Differentiate the numerator. There is no y here, so it will be 0. So the differentiation of this will give you 0. Minus, leave the numerator now. Differentiate the denominator. Differentiation of this with respect to y will give you 2y. So 2y. Then all over denominator squared. That is x squared plus y squared all squared. Okay, so you see that this one now, the answer is everything here is 0. I'm left with minus 2xy all over x squared plus y squared all squared. Okay, so now let us get this one, partial v, partial x, partial v, partial y, and see what will happen. So partial u, partial v now, partial v, partial x will now be the same process again. So leave the denominator, differentiate the numerator, minus, leave the numerator, differentiate the denominator all over the denominator squared. So leave the denominator, x squared plus y squared. Differentiate the numerator. Differentiation of this with respect to x, there is no x here, so it's 0. 0 minus, leave the numerator y. Differentiate the denominator with respect to x. I'm going to have 2x. Okay, then all over denominator squared. So what is our denominator squared? That is x squared plus y squared all squared. Okay, so you see that partial v, partial x will now be minus 2xy all over x squared plus y squared all squared. Okay, you sure I did not make mistakes somewhere? So let me check it out. Okay, okay, so I'm only human, make nobody bad. So where was I getting my question? I think it's from there. Okay, there was minus. The error here is that there was minus here. So go back and check. When we separated them, I think I forgot the minus there. When I rationalized, it was minus. Yes, because I rationalized with the conjugate, so it was minus. So there is minus here. So this minus, how is it going to affect the whole thing we have? Okay, it's going to affect only this thing, this one we are doing. So since there is minus there, so that means differentiation of so let's go again. Leave the denominator this. Differentiate the numerator 0 minus, leave the numerator. So if I'm leaving the numerator, I'm leaving minus y. Differentiate the denominator, I'm going to get 2y, 2x. So all over the denominator square. So here is going to be plus. Okay. So I noticed there's a mistake. So that's why I now decided to check. So finally, partial v over partial y will now be, leave the denominator, that is x squared plus y squared. Differentiate the numerator, you're going to have a minus 2, differentiate the numerator, you have minus 1, okay? Then minus, leave the numerator now, which is minus y. Differentiate the denominator, you have what? 2y. Then all over, differentiate the denominator, you have 2y. This one is 0, 2y. So all over denominator squared, x squared plus y squared all squared. So if you open this bracket, you're going to have minus times this will give you minus x squared, minus times this will give you minus y squared. Everything here will give you plus 2y squared. Then all over x squared plus y squared all squared. So this is going to give you that partial v, partial y will give you this, and this will give you y squared. So y squared minus x squared all over x squared plus y squared all squared. If you notice, what we want to check if partial u will be equal to partial u partial x will be equal to partial v partial y. So let's check it out. Partial u partial x gave us this. Partial v partial y gave us the same thing. So it has satisfied the first one. So we check for the second one. So partial u partial abnormal now, partial y will be equal to the negative of partial v partial x. So it means that there will be the same thing. The only problem is that the negative will be the problem. So partial u partial y is negative of this thing. Then partial v partial x is positive of the same thing. So they are the same thing but different in their sign. So it has satisfied the second one. So we conclude that that this function is analytic. So you conclude that this function is what? Analytic. So write it that f of z is analytic. F of z is analytic. Okay, so f of z is analytic. So let's solve I think one more question, then we'll now move to harmonic function. Then we're good to go. So just one more question so that I will not waste so much time. So your assignment is all those questions we solved, all those questions that we arranged in both, we arranged in the real and imaginary part. Each of those questions, check if they are analytic or not. Okay, each of those questions we solved that we changed into real and imaginary parts. So check if they are analytic or not. Very, very important. So check if they're analytic or not. Okay, so I'm going to solve the last one. The last one said that test for analyticity of f of z is equal to what? Log z. So let's check this one. So if I'm done with this one, I'm done with this particular one. We'll now go to harmonic function. So solution, remember that the first thing we do is to convert them into real and imaginary parts. That's the first thing you do. So we have that our log z is equal to, z is x plus y. So it's same as what? Log x plus yi. So if I separate this according to logarithm, it's going to be the same thing. In fact, before you separate it, change it to polar form. So if I change it to polar form, I have that this is log r in bracket of cos theta plus I sine theta. Don't forget. So let's change it to exponential form. Change it to exponential form is going to be log r exponential I theta. Okay. So now we know the law of logarithm that says that log a multiplied by b can be expressed as log a plus log b. So this one can be expressed as log what am I saying? Log r plus log exponential I theta. Okay, so this is something as saying log, remember what is our r? R is the modulus, which is x squared plus y squared, plus then theta will come I theta will come to the back, I theta log e. Remember, it must be base e because we are talking about natural log. So if the log and the base are the same thing, it's gone. So we are left with what? Log the root of x squared. In fact, let me use ln so that it will be easy. Because natural log is the same thing as ln. So this is natural log. So it's going to be ln the square root of x squared plus y squared. Okay? Then plus I theta. And remember, your theta is what? The argument. So I'm going to have that this is what? That my f of z is equal to what? Ln the root of x squared plus y squared. Okay? Then plus I tan inverse of x plus y. Okay? Or sorry, y plus x. Tan inverse of y over x, not plus. So immediately you express it in this form. So what do we do here? So obviously we have separated them. So you will now see that your u of x comma y, the real part is this one that does not have I, which is ln the root of x squared plus y squared. And then v of x comma y is this one that has I, which is what? The tan inverse of y over x. So you see that partial u partial x is equal to, so the differentiation of something is 1 over that thing. So I'm having x squared plus y squared. So but this is chain rule. So to differentiate this, 1 over that same thing. Sorry. So to differentiate the inside, you're going to have, with respect to x, is 2x here. Okay, so that is how we have 2x the root of this, right? Is that correct? No. This is function of a function of a function. So this is not correct. So first of all, we have to differentiate here before we differentiate here something. And differentiation of the root of x squared plus y squared is something as a differentiate this inside is 2x. Differentiate something that has raised to power half is to multiply by the half and remove 1 from the half. So I'm going to have okay, so this is going to be partial u partial x will now be, so multiply by that, this is 1 over 2, multiply by that 1 over 2, okay, remove 1 from the 1 over 2, so I'm going to have x squared plus y squared raised to power half minus 1. So which will finally give you, this is taking care of this, it's just giving me x over the root of x squared plus y squared. So to differentiate this one alone is x over the root of x squared plus y squared. Multiply by differentiation of lane something is 1 over that, is 1 over that same thing, the root of x squared plus y squared. So root times root 2 times root 2 is ordinary 2 without the root. So root this times root this is just that same thing without the root, that is x squared plus y squared without the root. So I've gotten my partial u partial x. So partial u now, partial y, should give us what? The same method. It's going to give us, the only thing that will change is here will now be y over x squared plus y squared. Okay? So it's the same thing. So we move to the next one, which is the other side, which is this side. We move to this side. So moving to this side, I'm going to be having my partial v partial x. Okay, so we go by partial v partial x. Okay, is equal to, first of all, we're differentiating the inside. Now, this is something as saying the tan inverse of y staying alone multiplied by 1 over x. So differentiation of 1 over x is minus 1 over x squared. You understand? That is x raised to power minus 1 is here. So multiply by the power minus x raised to power minus 1 minus 1, which is minus x raised to power minus 2, which is what? Minus 1 over x squared. So the differentiation of the inside will first of all give us minus 1 over x squared. Multiply by differentiation of tan something is I think 1 over 1 squared plus y over x all squared. Okay? So that is it. So this is going to be minus 1 over x squared multiplied by 1 over 1 plus y squared over x squared. So if you clear, this time this will give you minus 1 over, this time this will give you x squared, this time this will give you y squared. Okay? I hope I did not change anything. Okay? So I think there should be an error somewhere. Okay, sorry. When I differentiated this side, y is attached to it. Sorry. So you are differentiating here. Y is the coefficient. So the coefficient must be with it. The coefficient must be with it. So if I put that coefficient here, so I'm putting that coefficient here. So the coefficient must be with it. So that is why I'm going to have minus y. Okay, so here is minus y. So the next thing I'm looking at now is partial v over partial y. So partial v over partial y is differentiating y is 1. So 1 times the coefficient is still, you leave the coefficient 1 over x. So differentiation of tan inverse of something is 1 over 1 squared plus y over x all squared. So which will give us 1 over is there, I think I'm making mistakes somewhere. Okay, this is 1 over x. Let's check where the error is coming from. Is it 1 over x? Yeah, 1 over x. Which one am I differentiating? Y. Y is 1 over x. Okay. x over, I think there's a mistake somewhere. Okay. 1 over s in this. This is what it's supposed to be. Differentiate, you have 1 over s multiplied by differentiation of tan inverse of something is 1 over 1 squared plus that thing squared. So if you do this, if you do the math here, let me write it where you will see it very well. So let me clean here. Let me clean here. So I'm having this is tan inverse of y over x. So if I differentiate the inside, if I differentiate the inside with respect to y, I'm going to have 1 over x. So 1 over x multiplied by differentiation of tan inverse of something is 1 over 1 squared plus that in squared. Okay, so this is now 1 over x multiplied by 1 over 1 squared plus y squared over x squared. So this is 1 over x multiplied by 1 over, the LCM here is s squared plus y squared over x squared. So this one can go up. This one going up, I'm going to have 1 over x multiplied by x squared over s squared plus y squared. So I'm having x will take care of one of the x here. So I'm left with x over s squared plus y squared. Okay, and this is so this is what I got as this x over x squared plus y squared. So if you check it out now, you will see that we want to test if partial u over partial x will give us exactly the same thing as partial v over partial y. So let us check. Partial u over partial x gave us this. Partial v over partial y gave us this. Correct. So the first test is satisfied. The second one is partial u over abnormal. Partial instead of x, now partial y. Did they give me the negative of partial v over partial x? So let's check. Partial u, partial y gave us this. Partial v, partial x gave us negative of exactly the same thing. So it is now proved that what? That log z is analytic. So you now write that in conclusion, log z is what? Analytic. So the last thing I'm going to talk about is now harmonic function. Then I'm done with this particular video. So harmonic function. Okay, harmonic function. So now for harmonic function, it is very, very easy. What do we need to do? Harmonic function, to test if a function is harmonic. So right, a function is said to be harmonic if it satisfies the Laplace equation. So a function is said to be harmonic if it satisfies the Laplace, what am I saying? A function f of z, a function f of z is said to be harmonic if it satisfies, you know that a function is said to be analytic if it satisfies the Cauchy-Riemann equation. Don't forget. So a function is now harmonic if it satisfies the Laplace equation. And what is the Laplace equation? Now, Laplace equation is gotten from Cauchy-Riemann equation. Cauchy-Riemann equation said partial u over partial x is equal to partial v over partial y. And partial u over partial y is equal to negative partial v over partial x. So if we take the second derivative of both sides, I'm going to have that partial squared u over partial x squared is equal to partial squared v over partial y squared. Okay, let me call this equation 1. And then from this side, take the second derivative of this side. I'll have partial u over partial y, sorry, partial squared y like this, is equal to what? Negative of partial squared v over partial x squared. So if we add the two of them, let us add equation 1 and 2. So if I add equation 1 and 2, are we taking the second derivative with respect to what? Sorry, the mistake is with respect to x. I'm taking them with respect to x. So see what we are going to do. This one that has x, we will take its derivative with respect to x, and the other one with respect to y. So let me call this equation 1 and 2 so that it will make sense. This one is equation 1. equation 1. Then the second one, partial u over partial y is equal to negative partial v over partial x will now be equation 2. So we are going to differentiate equation 1 with respect to x. Okay, so if I differentiate equation 1 with respect to x, I'm going to have partial squared u over partial x squared is equal to what? Partial squared v over partial x partial y. Okay, so now we are going to differentiate. Let me call this equation 3. We are going to differentiate equation 2 with respect to y to have partial squared u over partial y squared is equal to what? Negative of partial squared v over partial x partial y. So let me call this equation 4. So we're going to add equation 4 and 5 to see our result. Adding equation 4 and 5, equation 3 and 4. Add 3 and 4. If I add equation 3 and 4, I'm going to have this plus this. That is partial squared u over partial x squared plus partial squared u over partial y squared is equal to, this one give us partial squared v over partial x partial y, plus minus will make a minus, so minus partial squared v over partial x partial y. See that these two is gone, they are opposite of each other. So I'm left with partial squared u over partial x squared plus partial squared u over partial y squared is equal to 0. So this is what we call the Laplace equation. So any equation, any function that satisfies the Laplace equation, we say that that function is harmonic. So we say that that function is harmonic. So we're going to solve just one or two examples. We are done with this particular video. Okay. So first example, they said given that u is equal to 2x in bracket of 1 minus y, they now say that show that u is harmonic. Solution. Okay, this one is a very simple question. Because of time, that's why I gave this one. So u is equal to what? 2x in bracket of 1 minus y. If I open bracket, you will see that u is equal to what? 2x minus 2xy. This time is 2x, 2 times 2xy. So we need partial u over partial x, which will give you, differentiate with respect to x. This is 2 minus, this will give you 2y. So partial u over partial, so the second derivative, partial squared u over partial s squared will now be, differentiate with respect to x, I'm getting 0 because there is no x here, 0. So we go by partial partial u over partial y. Partial u over partial y will give us, here is 0, here will now be just minus 2x. So partial squared u over partial y squared will give you, there's no y here, so here is 0. So if you check, 0 plus 0 is giving us 0. So it is now proved that this is harmonic because the addition of this is supposed to give us 0 and the addition of zeros is 0. So it is harmonic. So I'm going to solve just one more question and then I'm done. Just one more question. So, and the question here said that we should show that 1 over 2 log x squared plus y squared is harmonic. Okay, solution. So how do we do that? We are given that u is equal to 1 over 2 log x squared plus y squared. I don't like using this type of log. I like using ln. It is easier for me. So y is equal to what? 1 over 2 ln x squared plus y squared. Okay. So with this, what do? We take the first and the second derivative. So sorry, u, not y. So we're going to have partial u, partial x is going to be, differentiate this inside with respect to x. I'm going to have 2x multiplied by the 1 over 2 is already here, right? Then Differentiation of lane something is 1 over that thing. Is that correct? Yes, differentiation of something is 1 over that thing. 1 over x squared plus y squared. Okay, so this will give us 2 can take care of 2. I am left with what? X over s squared plus y squared. Okay, so let's take the second derivative. Partial squared u over partial x squared is equal to second derivative. We'll now use quotient rule. Quotient rule said leave the first one, leave the denominator, which is x squared plus y squared. Leave the denominator, differentiate the numerator, you have 1 minus, leave the numerator x, differentiate the denominator, you have 2x, then all over the denominator squared, s squared plus y squared, all squared. So if you do that, you're going to have minus 2s squared plus 2s squared is x squared. So I'm having y squared minus x squared all over s squared plus y squared all squared. So this is my second derivative. So I will now check for y now. So partial u over partial y, first derivative. So it's just to change y on the numerator. But differentiation of this will give you, okay, differentiation of the inside will give you 2y multiplied by 1 over 2 is a constant that is here. Differentiation of lane something is 1 over that thing. So 1 over that same thing, s squared plus y squared. So you see that 2 taking care of 2. I am left with y over s squared plus y squared. Okay, so with this, what do? We open bracket again. Sorry, we do the second derivative. Partial squared y over partial y squared will now be equal to, leave the denominator, s squared plus y squared. Okay, differentiate the numerator. If you differentiate the numerator, you have 1 minus, leave the numerator, y, differentiate the denominator, you have s squared plus y squared all over denominator squared, s squared plus y squared all squared. So if you look at this, you're going to have, I hope I'm correct, sorry, leave the denominator, differentiate the numerator, you have y, leave the numerator, differentiate the denominator, you have 2y, sorry, you have 2y. Okay, so if I open this bracket, I'm going to have that this is x squared minus y squared, because this and this will give you minus y squared all over s squared plus y squared all squared. Now, if I take out negative in bracket of minus times this will make it minus times minus will be plus y squared minus x squared all over x squared plus y squared all squared. So minus times this is minus times this is this one, minus times minus is this one. So if you notice that we want to check if we add partial squared u over partial x squared, if I add it with partial squared u over partial y squared, will I get 0? Now if you add this and this, will you get 0? Yes. Why? Because they are just opposite sign of each other. So as simple as that. What does it mean? It means that what this function is what? Harmonic. So thank you very much for watching. Please don't forget to like our video, share to your friends, subscribe if you are new to the channel. May the peace of the Lord be with you. Bye bye.